Alright, here I want to go over an example of how to deal with a non-zero R ratio when you're using a defect tolerant approach. So we have a problem set up here that we have Armstrong flooring plants and on their assembly line they have a bending member made of man-tin steel, and they give you the rectangular cross-sectional dimensions as defined in figure 813. So we have a width of 40 millimeters and a thickness of 10 millimeters. And we know that there is a through thickness edge crack of length 0.5 millimeters that we can detect. So if we can detect it, we have to assume that's our initial crack length. It tells us that the member is subjected to cyclic bending between a minimum moment of 500 and a maximum moment of 800 Newton meters. And it gives us the constants for man-tin steel. So we have C naught given in millimeters per cycle over megapascal root meters to the M. We have M, gamma, and the fracture toughness given as well. And it tells us, going ahead and, at least for the first analysis, assume that F is equal to 1.12 over the range of crack lengths. So that's that constant value for F when your alpha or your A over B is small. And that is a reasonable assumption here. At least when we start, we have an alpha of 0.5 millimeters over 40 millimeters, so that is very small. So one of the first things that we're going to have to do in this cyclic loading is figure out what is our maximum moment and what is our minimum moment, and how does that translate into a maximum and minimum stress. So they give us that we're cycling between 500 and 800 Newton meters. And so we're going to take that moment and turn it into a bending stress. And that's what we have here. So if you're looking at figure 813, you'll see that on that graph they say that SG, standing for the stress, I'm not honestly sure what the G is, the S is standing for stress, is equal to 6m over b squared t. And you might be saying, wait, where did that equation come from? That's out of left field. It's actually the same equation that we've been using. So if you look at my over I for this rectangular cross-section, m is the same. In this case, our y, or our distance from the neutral axis, considering the direction of bend, so that we're pulling open that crack, the distance from the neutral axis is actually b over 2. And then we have our moment of inertia, which is 1/12 base height cubed. Now in this case, again, with our orientation, base for us, quote unquote, is actually what they call the thickness. And then our height is actually what they call b. So if you look at it, this equation, which is my over I, is actually the same equation as 6m over b squared t, given their orientation and the way that they define things. So you can just jump to the 6m b squared over t, but make sure that you know where that comes from and you've convinced yourself that that's the same equation. So if we plug in the 800 and 500 Newton meters for that moment, we end up getting a maximum bending stress of 300 megapascal and a minimum of 187.5 megapascal. And that gives us a delta sigma of 112.5 megapascals. And for some reason, my R ratio is cut off here, but I think we find that the R ratio, according to down below, is 0.625. So the first step in one of these cyclic loading problems is just to figure out what's your sigma max, what's your sigma min, what's your delta sigma, and what's your R ratio. So we have all that done. So secondly, we're going to talk about assumptions. So the material is linearly elastic, isotropic, homogeneous. That all goes into using any of these material properties that are listed here. Those are the assumptions that underlie those. Those are also the assumptions that underlie our my over I bending stress. And we're assuming that the crack is on the tensile side of bending. It tells us as in figure 8.13, which depicts the crack on the tensile side. And for the first pass through here, we're going to assume that F is constant. So what do they want us to find? First of all, at what crack length is failure expected? So they're basically asking us to find a final. Secondly, how many cycles can be applied before failure? So that's essentially your NIF. And then we get into some sort of different variants on there that we'll come back to. So in terms of governing equations, again, we're taking Paris law, which describes that stable crack growth region in the DADN curve, which is basically a straight line on a log-log plot, which turns into this exponential form. And we're going to combine that with our stress intensity equation from LEFM. And when we combine those two and then we integrate, we get this expression here for the number of cycles until failure. And then we're also going to work a bit with safety factors. So for safety factors, we're essentially comparing the limit over like what we have. So the first question that they ask us is to find the final crack length. So again, this is the stress intensity equation solved for A, where we plug in the fracture toughness and the maximum stress. So when we do that, we get a final crack length of 112.8 millimeters. And you may just kind of plug that into the equation and go on ahead and plug and chug through there. Excuse me. But hopefully you're a good engineer and you say, wait a second, 100 millimeters, that's larger than our dimension of B, which is only 40 millimeters. So you should at this point kind of realize, oh wow, okay, the crack is not actually going to grow until it reaches a critical crack length. It's actually just going to grow until the part, breaks into two pieces. So at that point, then your final crack length is actually replaced by the width of the specimen. So just always check your final crack length that you solve for versus the width of the specimen. And so we know here that F is certainly changing. So that's a big kind of first pass assumption that we're making to use this NIF equation where we keep F constant. So let's look at this equation and plug in. So we're going to use that dimension B of 40 millimeters for our final crack length. It told us that initially we could detect a crack of 0.5 millimeters. So we put that into meters and we see that here. Our M is 3.13. That was given. And this is the C constant that gets pretty nasty when you have a non-zero R ratio. So it's the original C, or C naught, that was given, and I strongly suggest that you always work this in meters. So I always just take this and change this into meters per cycle. So it was given as 3.28 times 10 to the negative 9th millimeters per cycle. That would be the same thing as 3.28 times 10 to the negative 12th meters per cycle. A constant here, I want to scroll up so that we can see our constants that were given. This is going to be the C that now is adjusted for R ratio. So I strongly suggest that we keep our units in meters here and here. So I usually go and if this is given in millimeters per cycle, I take that, divide by 1,000, and I get 3.28 times 10 to the negative 12th meters per cycle. Then that is over 1 minus R, so you plug in 0.625 for R, and that is raised to the M times 1 minus gamma. And up here, gamma is given as 0.928. So a lot of times I'll actually pull this out and calculate this separately as one single value so that, again, if you're kind of comparing with friends or something on where you might have gone wrong, there's a lot of potential for sort of calculator error in this. And so that way I don't have to keep recalculating that, but I can do it once, check it a couple of times if I'm not getting the correct answer, and isolate my problem. So that's what's going to change in this analysis as compared to in the stent, is that instead of just putting in your C for this, now you have to put in C that's modified by this R ratio and now brings in this extra material property gamma. So once we have that, then the rest of the equation, we plug in F as assumed constant at 1.12. We plug in our delta sigma, which we found to be 112.5 megapascals. We plug in our square root of pi. All that is raised to the m. And then this exponent, which is 1 minus 3.13 over 2. So a lot of times when I'm solving these, again, I will also just calculate this as a single value that, again, I can easily check with people. It makes my calculator work a little bit easier, makes it a little bit easier to sort of isolate an issue or problem. So if you plug all that in correctly, you should get about 1.3 million cycles. So we're looking at over 1 million cycles for this particular scenario. So that answered how many cycles can be applied before failure. Now we're asking, assume that the member is subjected to 1 million cycles before inspection. What is the safety factor? Assume that the part requires a safety factor on brittle fracture of 3. What inspection interval is needed? So here we're working a bit with safety factors and inspection intervals. So we come down here, and the safety factor on life is going to be the 1.3 million cycles that we said that it would last, that is its limit of the material. So that's using that material property fracture toughness in terms of when we found the final crack length. So this is, you can think of as the limit, 1.3 million cycles. And it says, and for the inspection, we want to have 1 million cycles. So our safety factor is 1.3. So that's not great. So the second part of the question is saying we want a safety factor on this fracture of 3. So what is the inspection interval that we would need? So therefore, if we need a safety factor of 3 and it'll last 1.3 million cycles, we divide that by the 3 and we get that we need to inspect every 4.3 times 10 to the 5th